must be equal to BE. So how can we have that from these two relations, from these two equalities? AF must be equal to BE. If we multiply these two things, do we get anything? Let me just see. BCDE. Yeah, D is cancelled and C. We need AF, so that means we have to multiply by F. Okay. From this, we have AFD. Okay, we are considering this quantity AFD. Now AFD, in place of AFD I can write FAD because of commutativity, and in place of AD I can write BC using the first equation. And in place of, then I can rearrange this product like this, BCF, and in place of CF I can write DE, so BDE. Okay. Now, since D is not equal to 0, because you see, according to our definition of M, it contains or it consists of those ordered pairs where the second coordinate is non-zero. So here B, D, F, these are all non-zero. So the non-zeroness of D we can now use. Now since D is non-zero and capital D is an integral domain, AFD equal to BDE implies we can cancel D from both sides. AF is equal to BE. Hence, from AF equal to BE, you see, AF is equal to BE, we have this related to E comma F. So, this is transitive. And we have verified all the three properties for the relation to be an equivalence relation. Hence, this is an equivalence relation. In the next paragraph, we are going to devise a notation for the equivalence classes. Let this denote the equivalence class of A comma B belonging to M. So for every element in M like this, the equivalence class that contains that element will be denoted like this. Let F, or let me write it here, it will be more neat. let F denote the set of these equivalence classes. And this is our candidate for the field. So see, what we have done here is this. In M, I mean, if we go back to our original example of rational numbers and integers, in M we have things like this: 1, 2, 2, 4, and many other things. According to our definition of equivalence relation, these two things are related. Why? Because 1 times 4 is equal to 2 times 2. So they are considered to be the same thing, or they are considered inside one equivalence class. Now if I am in place of this notation, I use the other symbol 1 by 2, then this equivalence is just written like this. And all of these things, all the other elements in this equivalence class, they represent one single thing, and that is a rational number. So according to this construction, a rational number is not just a symbol which looks like this, but it is a set of such symbols, truly speaking, because this equivalence class is a set. In that set, we have all possible representations for the same rational number. Okay. So now next, what we to prove that F is a field, naturally first thing is that we have to define addition and multiplication. That's what we are going to do. We will now define an addition and a multiplication on F that will turn F into a field. Okay. For belonging to F, we define, see, in defining addition and multiplication, we will take our cue from the discussion that we had in the beginning. So this we are treating as nothing but A by A divided by B. So the definition for addition will be just this. AD plus BC, BD, and and the definition of multiplication likewise will be AC, BD. But having defined these things, we have to now verify that these definitions are well defined, because you see, we are not dealing with a single, of course we are dealing with single objects, but the objects have several different representations. if I have two pairs like this, A1 comma B1 and A2 comma B2 in M, and suppose that A1 B2 is equal to B1 A2, then A1 B1 is related to A2 B2, so they belong to the same equivalence class. As a result, we have these two different representations for the same equivalence class. So if we are defining the addition and multiplication like this, which representation shall we use, and ultimately shall we get the same answer? If not, then our definition is not well defined. It will be meaningless, because we change the representation, we keep getting some different answers, then it's not an operation at all. That's the first thing we have to verify, that these definitions are well defined. We now show that these operations are well defined. So for that, what we will do, it's that same thing, let A1 comma B1, A2 comma B2, C1 comma D1 and C2 comma D2 belong to F such that these two are actually equal, and these two are also actually equal. Okay. Now our aim is to prove that if we use this representation and this one and get some value for this sum, we will get the same thing if we instead use this and this representations. So that means we can see in advance what we want to do. We want this to happen, plus should be equal to C2 comma D2. So this means according to the definition, this is A1 D1 plus B1 C1 comma B1 D1. This should be equal to A2 D2 plus B2 C2. This is equal to B2 D2, and that amounts to showing that these two ordered pairs B1 D1 are equivalent. A2 D2, there is a high chance of making mistakes with all these subscripts. Okay, so I have to be extra careful. That means what? That means I have to show A1 D1 plus B1 C1 times B2 D2 is equal to B1 D1 times A2 D2 plus B2 C2, and this implies I have to show A1 D1 B2 D2 plus B1 C1. I am running out of space. Let me write from here. Okay. First, let us see what we have to do, and then we will do it. So this implies I need A1 D1 B2 D2 plus B1 C1 B2 D2 should be equal to B1 D1 A2 D2 plus B1 D1 B2 C2. Is this true? That is the question. Now let's have a look at these relations. What we already have assumed. We started with this. So this one means A1 comma B1 is related to A2 comma B2, that is, which is equivalent to this statement that A1 B2 is equal to B1 A2. Similarly, from this one we get C1 D2 is equal to D1 C2. Now let's look at this. A1 D1, okay, but here we have A2, okay, A1 D, okay, yes. You see, this term can be written like this: A1 D2, and what we are left with, not D2, sorry, B2, sorry, A1 B2 D1 D2. On this side of equality, here we have B1 A2 D1 D2, and these two are equal because D1 D2 are already there, and A1 B2 is equal to B1 A2 from there. Like that, this term is, here we have B1 B2 and C1 D2, and here we have B1 B2 and D1 C2. So C1 D2 is equal to D1 C2. So it actually is the case that these two are equal. Now we can do the back calculation. For the sake of completeness, I have to actually write all these things, since this is just a rough work. But I think I will definitely forget I need this, so let me not wrap this one up. Let me start from here. These things also, okay, see, that is the problem. When you write formally, it looks as if you already know everything and you are just simply writing. That's not the case. We can't remember everything. I mean all the symbols where everything occurs, etc. Sometimes we have to do back calculations like this. So from after this we can continue like this. From these relations we have we can shorten the situation. Instead of writing that the ordered pair a1 comma b1 is related to a2 comma b2, we can straight away write a1 b2 is equal to b1 a2. It's understood how this is reached, and c1 d2 is equal to d1 c2. Hence now we will directly write this a1 d1 b2 d2 plus b1 c1 b2 d2 is equal to b1 d1 a2 d2 plus b1 d1 b2 c2, and this implies b2 d2 can be taken common out. a1 d1 plus b1 c1 b2 d2 is equal to, or let me write here for the sake of clarity, the hell, here the common thing is b1 b2 b2 or what is it, d1 d2 b1 d1, okay. a2 b2 plus b2 c2. Note that it is because of these relations that we have this equality. Okay. Now this implies a1 d, I think I need ink. So a1 d1 plus b1 c1 comma b1 d1 is equal to a2 b2 plus a2 d2 b2 c2 comma b2 d2. This is the condition that tells us that sorry, these two are not equal, they are related. See how quickly we can make mistakes. This implies the equivalence classes containing these ordered pairs are equal. Now this is nothing but a1 comma b1 plus c1 comma d1, and this is nothing but a2 comma b2 plus c2 comma d2. So addition is well defined. On F is well defined. Similarly, we will now show that multiplication is well defined. That will be somewhat easier because definition of multiplication is easier than that of addition. So here what we need, again we can see, we can do a similar calculation here. But now that we have seen the calculation for addition, or rather the back calculation, we can be somewhat more sketchy with multiplication. So we want a1 comma b1 times c1 comma d1 to be equal to this. That means we want a1 c1 comma b1 d1 to be equal to this, or a1 c1 b2 d2 should be equal to b1 d1 a2 c2, right? Now yes, we have a1 b1 is equal to a1 b2 is equal to b1 a2. That we are having from the relation that we already have. I rubbed it off. Anyway, like that we have c1 d2 is equal to d1 c2. So this is indeed true. So we are going to start from here. Next, from a1 b2 is equal to b1 a2 and c1 d2 is equal to d1 c2, we have, just we have to write these things in the opposite order. a1 c1 b2 d2 is equal to b1 d1 a2 c2. This implies a1 c1 comma b1 d1 is related to a2 c2 comma b2 d2. This in turn implies, and this is nothing but the product of a1 comma b1 and c1 comma d1. Like that, this is the product of a2 comma b2 and C2 comma D2. So multiplication is also well defined. Now we will verify the properties or the axioms that will tell us that with respect to these two operations f is a field. Okay, so let us go one by one. Okay, let a b c d e f. Oh, by the way, I forgot to mention one thing. I should have mentioned that before saying that these operations are well defined. See, after you write, did you notice one thing? Although we are considering equivalence classes like this, but the second coordinate of any representative is non-zero. So when I am defining addition, say I am defining addition like this, AD plus BC comma BT. For this to again be an element of F, this has to be non-zero, because otherwise it's meaningless, no? Just like that, this again has to be non-zero. Luckily, since we are in an integral domain, and according to my definition, B is non-zero and D is non-zero, and in an integral domain the product of two non-zero elements is non-zero. That's why I have BD is also not equal to 0. So you have to insert this somewhere. I mean, somewhere means before you write, so the addition on F is well defined. Before that you write this fact, you try to write it nicely, that since B and D are non-zero, note that BD is also non-zero because we are in an integral domain. So that's why not only is this operation independent of the representative we are using to represent the equivalence classes, but the result is actually in F. Similarly, in case of multiplication also you write the same thing. I am not going to modify this part, okay. I just simply mention this so you fill in those things, those gaps, okay.